Hi ROS developers, and welcome to this new ROS Projects video. If you want to learn anything about ROS, this is your channel. You can learn about navigation, about drones, about autonomous cars, everything ROS. You can find it here. And you can find videos that teach you step by step very basic concepts, from very basic concepts to very high quality and quite demanding topics. So you'll find practically any topic in our channel, so please check it out, and you'll be surprised of how much you'll learn in just 10 or 30 minutes. So just before we start, if you want a more guided experience, I highly recommend you that you visit our Robotics Academy, where you will find courses about ROS on many subjects, no installation required, and you will be able to use simulations without any installation whatsoever. So you'll find a link in the video description. And without further ado, let's get started. So let's have a look. So let's have a look first to the class. So you have to create a class. The name doesn't matter. And we initialize. The first thing is that we have to check that all the sensors are working. And you'll say, well, yeah, supposedly they work. Well, in ROS, not always. And so the thing is that you have to check that these topics that you're going to use, which are the joint states and the odometry, are publishing, because maybe you execute this code and, for example, the simulation is not ready yet, or your real robot is not ready yet. So you need to do these checks, because afterwards you need the data to be always updated. You can't wait for the data to come. It won't work, because you won't have the state updated, and that will generate problems in the calculation of the rewards, and then it won't learn correctly, a mess. So check that the sensors. And how do we do it? Well, let's have a look. So first things is we do a while this variable is none, then we continue, or if you Control-C the Python script, basically. And what we do is we try to wait for a message of this topic, which is one of the two topics that we talked about the sensor data coming from, which is joint states, and the other one is odometry. And then the type of the message and the timeout. If you have any doubts of how this works, please, I highly recommend you that you do this course on ROS Basics in 5 days for Python. It's super useful, and you'll understand every detail and everything that I talk about in these videos. So if you don't understand these concepts, please have a look at this course, okay? So let's continue. So we try it. If there's a timeout, if 1 second passes in this case, then we do an exception and we say it's not ready, and we try it and we try it again until it's ready. Yeah, and we do the same thing for the odometry. Yeah, clear? Okay. So now we check the sensors. Now we can generate the subscribers without any doubt that the topics are working. So we now have a subscriber with a callback that will basically, here you go, the two callbacks will basically store the information in the class, and you'll have access to it every time that you ask for it, and it will be updated maximum. Okay, that's for the sensors. Now for the publishers. The publishers is the other way around. So first things, we have to create the publisher, which is, I want to publish here which is the topic where the controllers are listening to for the speeds. Yeah, because remember that we did a speed control in the simulation. So if you go here, just to show you, just to refresh your mind, the moving cube, we used a velocity controller to do this. Yeah, and the topic is inertial wheel roll joint velocity controller. Yeah, which is this inertial wheel roll joint velocity controller, and then the command. Okay, it's a float 64 and only a queue of 1, which is good because you don't have a very big queue. It always kills the stuff that builds up. Yeah. Okay, and then we have to check that this is running because we want it to publish each and every one of the commands that we send. So we use this function, which is check publishers connections, and we create this function which is at the rate of 10 we check that the number of connections of this publisher is different from 0 basically. Okay, or we control C. So we check and we sleep. This sleep is just to not ask it like every time. So to control the asking system, the asking rhythm. Okay, and that's it. Once we have it, we are sure that we can publish there and the messages won't be lost. Yeah. Okay. So I think that's it. We have it all initialized and we have all the systems. Now comes the AI part, which is the last part of this video, which is, okay, how do we move it? We publish in this topic. Okay, if you don't know how to publish a topic, please do our course. You'll understand it perfectly. Now we need these 3 functions that we do are the basic core of reinforcement learning, which is getting your state, knowing if it's done or not, the episode, and the reward of doing the actions that you did before. Yeah. The first thing, get the cube state. What's the state? The state is the data that you want to know about the system. It doesn't have to be all the sensory data, just the one that you are interested in or is useful for you for the learning. Okay, that's why I talked that it's not necessarily the speed of the odometry, for example. We don't need it, but just because it's a decision that I took. So what's the cube state? What does this return? Well, the cube state is, you can see here, a kind of velocity. What's this? This is the joint velocity, so how fast the wheel is spinning. This is one. The other one is distance. What's this, the distance? Well, the distance, we are calculating it based on the start position and the position of the odometry. So where is the cube now? And the distance from the origin in this case, because start position is the 0, 0, 0, which is the origin of the world, which is here basically, where these 2 white lines cross, intersect. Okay, we have the distance with this handy dandy function, which I'm using NumPy. We are transforming these vectors, or these points in this case, into a NumPy array, and this we are calculating the distance. Easy, right? As I said, all the code, you'll have it in the Git, so don't worry. Just try to understand and follow me if you can. So once we have this, okay, we have the distance, yeah, so it's our state. Then next elements, the orientation. We need to know how the cube is positioned, it's oriented, to know if it's upside down, and to calculate rewards for example, Do we want it to move only in one direction? I would assume that we want only one direction with this, only one disk. So if, for example, it's moving, let me show you. So this is the roll, the red ring, then we have the green ring and the blue one. So we wanted to turn around the red ring, which is the roll. That's why we painted this disk red. Yeah. So for example, we could give rewards for only turning in this direction, in the roll. And if it turns for any reason in the other directions, we can penalize it. Yeah? Okay. That's why we're adding it. Okay. So, now we have this. And how do we get this? Well, it's not trivial because the odometry gives you in Quaternions. So you have to turn it to Euler. Okay? There's a function in TF, which I'm importing right here. TF transformations, Euler from Quaternion. If you want to know, I'll leave how this works. I'll leave a very good video explaining only this topic. And yeah, if you don't understand how it works, just have a look at the video. And then this, we just pass it here. And one last thing, you see that I'm rounding. This is used to only have one decimal point. And you say, man, you need more decimal points. Well, we are trying, it's very important in learning, in AI, to minimize the quantity of data that you need to learn. Because if you have less data, you'll learn faster. So you can make the test, but basically we're moving in speeds for around 100 to 0, so very high speeds. So decimals really are not needed. So we could put here 0 perfectly. Then the distance, it doesn't matter if it's 2 meters 21 or 2 meters 22. It doesn't matter. We need to know more or less if it's like 2 meters and a half, 2 meters 8. That's what we need. So we don't need more. And the roll, exactly the same thing. Radians, it's only 0. I don't know, like 0.7. It doesn't matter if it's 7.1, 7.8. It doesn't matter for me in this particular case, okay? Because we don't need that precision. Yep. That's for the state. And now we calculate, so we go here, and once we have the state, we do the observation checks, which is the experiment finished? So in this case, we are going to consider that if it moved more than 2 meters in the learning, it's finished, the episode, for example. So what we do is we go to the cube state and we go to the element in position index 1, which is the distance, and we say, okay, if it's bigger than the maximum, which is 2 in this case, we say, hey, done is true. It's too far. If not, it's not too far. Easy, okay? And now, once we have this, we now calculate the rewards. The rewards, we use the state, the same thing, but now we decide, okay, what do we want to give positive feedback, reinforcement to the robot? So let's say, yeah, you did it very good. That's positive reinforcement. So the robot says, okay, that's good, so I'll repeat it, or I'll do this more often. Or negative reinforcement, so don't do this. So for example, in this case, as example, but you can try other rewards, and I highly advise you that you try it to see more or less what you get here. In this case is, I want it to move distance, as much distance. If it moves more distance, I'll give it more points per action. So if doing this it moves more, then I'll give it more points. Yeah. And here is a reward against speed. So if it can move with, instead of 100 of speed, it moves with 50, better, because it's consuming less energy and it will move more naturally, for example. And that's why we do the absolute of the speed, so it doesn't matter the direction, and we convert it to negative. And this will add up into the reward. And this is the reward. Yeah? Fantastic. So at the end, we're going, for example, to say, okay, let's change this. Let's do, for example, I don't know. Let's do, for example, 100. Oh, sorry. And that's it. And then 0, for example. Let's see what it does. So let's execute this. Wait a second. There we go. Clear. Go. Whoa. Okay. Okay, the reward is 3. Why? Because we got reward by distance. Reward by distance is 3 because, you see, cube not too far, 0.3. So it moved a bit. Okay. Let's try another thing. For example, let's try move 100. Let's put, for example, like 80, and then minus 80, and then 0, for example. So let's try it again. Oh, that's another thing. Yeah, it seems to work better, right? At least it moves. The reward too. Okay, it's because it's closer to here. Okay, yeah. And reward for effective movement 0. Why? Because we are always at the end staying at 0 of speed. That's why. Let's try it again. Great. Reward, now we have bigger rewards. We're moving further, that's good. So this will make it learn to go further and further. So you're going to, basically we're telling him, you're doing it very good. Fantastic. So again, so where is our distance? So it's 1.2. So for example, let's change the done function so that at, I don't know, like 1.3, it says that it has finished. There you go. So it said cube too far, 1.5. Perfect. So basically this is a very simple way of showing the procedure that the learning algorithm with QLearn or the OpenAI environment will do when we generate it. It will do exactly this. It will make an action, then see the reward and adapt to the reward. So if it gave a very big reward, then we continue doing that. If it gave bad reward, then it won't do that. Okay, it's basically that. And I think that's quite it. So if you didn't like the video, thumbs down. But if you liked it, thumbs up. It helps a lot. And consider subscribing to our channel. We publish videos every day. And I left all the information you need to reproduce this, the Git, and so on. And also a link to the courses in the description of the video down below. And see you in the next video. Hasta la próxima.